Welcome to This Explainer. Today, we're diving deep into the absolute ultimate cosmic mystery, breaking down the incredible physics behind black holes. If you've ever looked up at the night sky and wondered about the most extreme, mind-bending objects scattered throughout our universe, well, you're in the exact right place. We're going to peel back the layers of science, history, and pure mathematics to reveal what is actually hiding in the dark. All right, let's just tackle the biggest myth right out of the gate. Are black holes just giant cosmic vacuum cleaners aggressively sucking up everything in the universe? Pop culture absolutely loves to portray them this way, as these malicious whirlpools destroying everything in their path. But as we're going to see, the actual physics of how they operate is much more elegant and, frankly, way more fascinating than that. Here's the reality. They aren't empty holes or vacuums at all. A black hole is actually a region of spacetime where gravity is so unbelievably powerful that absolutely nothing can escape it. And I mean literally nothing, not even light, which travels at a blistering 299,792 kilometers per second. Once anything crosses a very specific invisible boundary known as the event horizon, it is permanently trapped. So here's our roadmap for today. We've got 1. Demystifying the black hole. 2. Gravity, spacetime, and Einstein. 3. Escape velocity and critical limits. 4. Crossing the event horizon. And 5. Observing the invisible. All right, Section 1. Demystifying the black hole. To really picture what we mean when we say they aren't vacuum cleaners, just imagine this. If our sun magically and suddenly turned into a black hole right this second, but kept its exact same mass, Earth wouldn't get sucked in. Now, we'd freeze, for sure, which is obviously a terrible day for humanity, but orbitally speaking, Earth would just keep right on orbiting exactly like it does right now. You see, gravity depends strictly on mass, not on whether the object you're orbiting is a glowing, burning star or a dark, collapsed black hole.
Moving on to Section 2, Gravity, Spacetime, and Einstein.
Understanding gravity is absolutely crucial here, and comparing Isaac Newton to Albert Einstein gives us the ultimate turning point in astrophysics. For the longest time, Newton's view completely ruled science. Gravity was just a pulling force between masses, right? It explained the falling apple, it explained Earth's orbit, but it kind of fell apart when dealing with the extremes of the cosmos. Enter Albert Einstein in 1915. His general relativity completely revolutionized physics by showing that gravity isn't a pulling force at all. Instead, mass and energy physically bend the 4 dimensions of spacetime. That's length, width, height, and time. Objects are literally just following the curves created by that bending. If that sounds a little abstract, the classic rubber sheet analogy clears it right up. Imagine spacetime as a tightly stretched rubber sheet. Plop a heavy bowling ball representing our massive star right in the middle, and the sheet naturally bends downward. Now, if you roll a small marble representing a planet nearby, it doesn't just go in a straight line, does it? It curves toward the bowling ball. The ball isn't pulling the marble, it's warping the space around it. A black hole is basically the absolute most extreme distortion of this rubber sheet known to science. Which brings us to Section 3, Escape velocity and critical limits. So let's talk about escape velocity. To leave any celestial body, you've got to hit a very specific speed to overcome its curved spacetime. Take a look at these numbers. The moon is pretty small, so its escape velocity is a modest 2.38 kilometers per second. Earth, that takes 11.2 kilometers per second. But the sun, with all that massive bulk, requires a staggering 617 kilometers per second just to break free. The math here tells us 2 very important things. More mass creates stronger gravity, but also a smaller radius creates stronger gravity. And scientists have been piecing this exact puzzle together for centuries. Wildly enough, back in the 1700s, John Michell actually proposed the idea of a star so compact that light couldn't escape, centuries ahead of his time. Then, following Einstein's 1915 breakthrough, a physicist named Carl Schwarzschild took those equations in 1916 and solved the math for what we now call a critical radius. He discovered that if you compress any object small enough, its escape velocity will eventually surpass the speed of light. Now, what happens if we apply that math to our own planet? Just to give you a sense of this insane scale, let's say you wanted to turn Earth into a black hole. Remember, you don't need to add any mass, you just have to compress it. According to the Schwarzschild radius, you would have to take the entire mass of the Earth and crush it down into a sphere of just 9 millimeters. That is roughly the size of a single glass marble. It's mind-blowing. And the scale gets even more unbelievable with stars. Our sun has a massive radius of 696,000 kilometers. But if you wanted to trap light and turn our sun into a black hole, you'd have to compress all of that unimaginable, fiery mass into a tiny sphere just 3 kilometers across. Once an object is compressed down inside that critical Schwarzschild radius, it fundamentally changes the fabric of reality around it. It forms an invisible space-time boundary called the event horizon. This is it, the absolute point of no return. And it's not a physical, hard surface you can touch, but a mathematical boundary in space-time. Once anything, a spaceship, a planet, even a beam of light, crosses this boundary, it is entirely cut off from the rest of the universe. No escape is possible, and no information can ever return. So Section 4, crossing the event horizon. What would it actually be like to cross it? Well, this perfectly highlights the mind-bending reality of Einstein's relativity. Let's say you bravely, or maybe foolishly, flew a spaceship straight toward an event horizon, while a friend watched from a safe distance. From your perspective, time feels perfectly normal to you, and you just endlessly keep falling inward toward the dark center. But your friend's perspective is entirely different. Because extreme gravity heavily distorts time and light, they'd literally watch your spaceship appear to slow down. You'd become redder and dimmer, and to them, you'd actually never seem to cross the event horizon at all. Your image would just permanently freeze and fade right on the edge of the boundary. Crazy, right? But if light can't escape and the event horizon is invisible, how do we know any of this is actually real? That brings us to Section 5, observing the invisible. Astronomers have actually categorized a few different types of these invisible giants. We've got stellar black holes, which form from collapsing stars and sit around 3 to 100 times the mass of our sun. Then there are intermediate ones, though they're pretty rare. Scaling massively up, we hit the supermassive black holes, millions to billions of solar masses. These are the giant anchors right at the center of galaxies, including our own Milky Way, which hosts a 4 million solar mass giant named Sagittarius A star. And lastly, there are hypothetical primordial black holes, which might have formed right after the Big Bang, though those are still unconfirmed. Now, since we obviously can't just look through a telescope and see the black hole itself, we have to look for its extreme effects on the surrounding universe. Step 1 is orbital tracking, basically finding stars whipping around massive, completely invisible spots in space at terrifying speeds. Step 2 is detecting X-ray emissions. As gas falls toward a black hole, it violently rubs together, gets superheated, and blasts out intense X-rays right before crossing the horizon. And step 3, which we first achieved in 2015, is measuring gravitational waves. These are literal ripples in the fabric of space-time, created when two giant black holes crash into each other. All that incredible, multi-layered detective work finally culminated in 2019. The Event Horizon Telescope collaboration, this massive global network of observatories, released humanity's very first direct visual evidence of a black hole. This right here is M87 star, located a staggering 55 million light-years away. This is a literal milestone in human history. That bright, glowing orange ring, that's the superheated gas we were just talking about, violently swirling around just outside the point of no return. And that dark center, that is the absolute, literal shadow of the black hole's event horizon. You are staring at an invisible monster 6.5 billion times the mass of our sun, a place where the math of Einstein and Schwarzschild becomes a visible, terrifying reality. And that really leaves us with this final thought. Black holes completely challenge our understanding of reality. They aren't just cosmic monsters. They are the ultimate natural laboratories, where the very laws of physics are pushed to their breaking points. They are our gateways to understanding gravity, quantum mechanics, and the evolution of the universe itself. So if we can now photograph the unphotographable, we really have to ask what other deep secrets of modern physics are hiding in the dark, just waiting for us to discover them next. Thanks so much for joining me for this explainer. Keep your curiosity sharp, and I'll catch you in the next one.